We are on Unit 1-3. We're going to begin to talk about angles. And remember, in geometry, when we make a definition, it tells us how to draw something. So if we think about it, about what an angle is, we would have a point, and then from that point, we would draw two rays. So an angle is a figure formed by two rays with a common endpoint. A figure formed by two rays with a common endpoint. The two rays are called the sides of the angle, and the common endpoint is called the vertex. So an angle is a figure formed by two rays with a common endpoint. Again, the two rays are called the sides, so one of the sides is ray AB. Remember, we name a ray with the endpoint first and then a point on the side second. And the other ray then would be ray AC. The vertex is that common endpoint, point A. You can name an angle by its vertex if it is the vertex of only one angle, as this one is, so we could call this angle A. We could name it by a point on one side and then the vertex in the middle and then a point on the other side, so we could call it angle BAC. Or we could start on the other side and call it angle CAB, again with the vertex in the middle. Or there might be a little number in the corner, not a degree measure, but a number denoting that as being angle 1. So we can name an angle by its vertex, if it's the vertex of only one angle, by a point on one side, then the vertex in the middle, and a point on the other side, or by a number that is in the corner. When we think about the measure of an angle, we're kind of thinking about a protractor or a semicircle. And so on a protractor, we start with 0 and we go to 180 degrees. And so we would be thinking of an angle's measure as being the amount of rotation between the rays in a circular motion. So an angle measure is the amount of rotation between its rays in a circular motion. We normally think of an angle in standard position as being where, if we did have a coordinate plane, where this was the x-axis and this was the y-axis, as the vertex of the angle being the center and the initial side as being a part of the positive x-axis, rotating counterclockwise with the terminal side of the angle being out there somewhere. So normal or standard position of an angle would be like that, where we actually rotated counterclockwise to open those two rays up to give that thing some angle measure. Okay? Now, postulate 1 says that the measure of an angle can be calculated somewhat like the ruler postulate. You remember the ruler postulate, where the distance between 2 points on the number line was equal to the absolute value of the difference of the coordinates of the point? Well, the protractor postulate, which is postulate 1-4, actually tells you how to use a protractor. And it says this. It says, given a line, let's call that line AB, choose a point O that lies between point A and point B. Consider ray OA and ray OB and all of the rays that could be drawn from point O on one side of AB. These rays can be paired with whole numbers between 0 and 180, such that one of the rays, like OB, is 0, and the other ray, like OA, is 180 degrees. If ray OP, some ray out here, was uh, associated with X degrees, and another ray out here, like ray OQ, was paired with Y degrees, then it says that we could find the measure of this angle POQ, by taking the absolute value of the difference in X and Y. So it looks like the ruler postulate, where you take the absolute value of the difference of the coordinates of the 2 points on a ruler. You're just now taking the absolute value of the difference of the coordinates of where your protractor hit. Now, normally when we measure an angle with a protractor, we set the initial side at 0, and then wherever that other side hit is the angle. So if we were going to actually measure angle POQ, we would actually set our protractor like this. Let this be 0, and then wherever P hit would actually be the measure of the angle, and we wouldn't have to go through that subtract and take the absolute value situation. Okay? All right, so postulate 1.4 says that to find the measure of an angle, you take the absolute value of the difference of the measures of the rays where it hits. And what this says here in fine print is ray 1 minus ray 2, or the P minus Q over there, okay? All right. Now we're going to get into specific types of angles based on the size of that angle. An acute angle is an angle whose measure is less than 90 degrees. An angle whose measure is less than 90 degrees, and so we could say between 0 degrees and 90 degrees. Now, when we say between 0 and 90, it does not include the 0 and it does not include the 90. And one example of an acute angle would be 60 degrees. Visually speaking, 90 degrees is like that. And so an acute angle would be anything less than straight over and straight up, right? A right angle is straight over and straight up as we would visualize it. Its sides are perpendicular, as we call it. The symbol for a right angle is a little box in the corner of the angle, as we've denoted over here also, and it is exactly 90 degrees. So all of our definitions are basically based on straight over and straight up. A right angle is straight over, straight up, where the rays of the angle are perpendicular. An acute angle then would be less than straight over, straight up, or somewhere between 0 and 90, not including 0 and not including 90. The word acute itself means small, or just a little bit. You may go to the doctor and they may say, well, you have acute bronchitis, which means you just have a little touch of bronchitis, okay? Obtuse comes from the word obese, meaning large. And so an obtuse angle would be more than straight over, straight up, or more than 90 degrees. But it's limited to being less than a semicircle, less than a straight angle. So an obtuse angle is going to be somewhere between 90 degrees and 180 degrees. And remember that when we say between this and that, it does not include those two items. So an obtuse angle is an angle whose measure is between 90 and 180, which again does not include 90 and does not include 180. An example would be an 150 degree angle. And then when we go straight across, we do have an angle because we have a point and we have rays going in opposite directions. Remember, those are called opposite rays, two rays with a common endpoint that go in opposite direction, and those form a straight angle, and a straight angle is exactly 180 degrees. Now, if two angles, external sides, form a line and they are adjacent, then we would know obviously that the sum of their measures is equal to 180 degrees. We say that those are a linear pair, a linear pair. A linear pair is a pair of angles whose external rays form a line. Because of that, because they make a straight angle whose measure is 180, then we can say that a linear pair adds up to 180. Okay? So we've got acute, which is between 0 and 90, doesn't include either one. Right angle is exactly 90. An obtuse angle is between 90 and 180, does not include either one. A straight angle is exactly 180 degrees. A linear pair is a pair of adjacent angles whose external rays form a line, and we say that then because of that, that a linear pair is a pair of angles that add up to 180. Now, not all pairs of angles that add up to 180 are called linear pairs. In fact, the set of all angles whose sum is 180 is called supplementary angles, right? Any two angles whose measures have the sum of 180 is said to be supplementary. So we could say then that linear pairs are supplementary. All linear pairs are supplementary, yet not all angles that are supplementary have to be linear pairs, we could say. Okay. All right, so now we're going to talk about congruent. We've already used the word adjacent, which we haven't formally defined, but we will here. Now, remember we talked about the equal sign and the squiggly sign and the equal sign with the squiggly sign and then this symbol and this symbol. I believe we talked about it so far. I've been teaching algebra and geometry both, and I can't recall exactly how much of this I talked about with you, so we're going to talk about it again. An equal sign is the same amount of bigness on both sides of the symbol. It actually represents the concept of same size. This little squiggly, this is an equal sign, by the way. The little squiggly symbol is a similar symbol, and it represents same shape, same shape. So things that are shaped alike, but one may be larger than the other, you probably remember words like dilation, to enlarge or reduce, to scale up or scale down, would create similar figures. So when we put an equal sign with a squiggly, we have both same size and same shape. The same size comes from the equal. The same shape comes from the similar symbol. If it's both the same size and the same shape, we say that it is congruent. This symbol has a big end and a little end. The little number goes on the little end and the big number goes on the big end. In the English language, we read from left to right. So as we read into that, we would read into the big part. And so we would say greater than. This symbol has a little end and a big end also. In the English language, we read from left to right, so when you read into it, you would hit the little end, and so we would say less than because we ran into the little end. So there's a little bit of information about the symbols. So when we think about congruent, we're thinking about same size and same shape. So congruent angles would be shaped alike, but they would also have the same measure. You can try to take two angles that have the same measure and make them not be shaped alike, but you can't do it. So congruent angles simply have the same measure. By default, they're going to be the same shape. So sometimes in this text, I will say that two angles that have the same measure are equal instead of saying that they're congruent. The congruent symbol looks like that. Since by default they're going to be the same shape, then I find it simple enough to say that those two angles are equal rather than going to the extent of saying that they are congruent. Okay? So I might say in this text that two segments are equal because they're the same length, and it's kind of given that two segments are the same shape. I would say that two angles that have the same measure are equal rather than congruent because it's kind of a given that they have the same shape. Now, when we get to triangles and polygons, then I would, in this textbook, begin to use the word congruent because the shape is not necessarily understood to be the same in those different types of figures, okay? Adjacent angles. Now, there's four properties of adjacent angles. They have a common vertex, a common side, they are coplanar, and they have no common interior points. Now, usually when I say the definition, I say it in this order. Adjacent angles are triangles in the same plane with a common vertex, a common side, and no common interior point. So I usually start out with two angles in the same plane with a common vertex, common side, no common interior points. Now, this is an example of adjacent angles, and let's see how those four properties apply. First of all, they're in the same plane, same flat surface. They have a common vertex. The vertex of angle 1 and 2 are the same, you can see. They do have a common side. This ray in the middle is a side of angle 1. It's also a side of angle 2. And then we could say, well, the angles on the interior of angle 1, the points on the interior of angle 1 were there. The points on the interior of angle 2 were here. None of the points of angle 2 overlapped into the region that was angle 1. And so we can say, well, those are adjacent. Two angles in the same plane with a common vertex, a common side, but no common interior points. And you realize I'm dealing with some inaccuracy here, so it looks like they had common points and they really don't. Okay. When we look at these other examples, the first one we can say, well, those are coplanar. The second pair are coplanar. The third pair are coplanar. So that doesn't rule any of those out. So according to that definition, this example of things that are not adjacent, they were not negated because of the coplanar. What about common vertex? Well, this one has a common vertex. These do not. The vertex of 1 is down here and the vertex is 2 is here. So these are ruled out because of the common vertex theory, so that's gone. Angle 3 and angle 4 have a common vertex, so they're still in. So now we've got the first example and the third example still in, with the middle example there gone because it was eliminated because there wasn't a common vertex. Now let's look for a common side. The sides of angle 1 in this particular drawing are here. The sides of angle 2 in this particular drawing are here. They did not share a common side, and so those were ruled out because of the common side part of the definition. Well, does angle 3 and angle 4 here have a common side? Well, angle 3 is this angle, and angle 4 is the whole big angle, which shared that common vertex. They do have a common side over here. So this example to the right, they are coplanar. They do have a common vertex right there. They do have a common side right there, but the points on the inside of angle 3 are here. The points on the inside of angle 4 all the way across. And so the points in here are common interior points. We're not supposed to have any of those, so that one got kicked out because angle 3 and 4 overlap. They had common interior points. So again, what are adjacent angles? Two angles in the same plane, the same flat surface, with a common vertex, a common side, but no common interior points. So one would be there, and one would be there. And a more formal definition of adjacent, you might be thinking side by side. But remember, when you're thinking side by side, you can't be thinking that where there's a gap in between, and you can't be thinking where they overlap, okay? Any questions on adjacent angles? The bisector of an angle. Now, we talked about the midpoint of a segment, and we know that it was the point in the middle. But if you define the midpoint of a segment as being the point in the middle, all you really did is rewrote the term itself. In other words, if I call this AB, and I say, what is the midpoint? You say, well, it's the point in the middle. Well, midpoint, point in the middle. All you did is restated the term. You didn't tell me what it does. What does that midpoint do? That's what I want to know. The midpoint of a segment is the point that divides a segment into two equal segments. Now, I got something out of that. Okay? So that's how we define a midpoint, the point that divides a segment into two equal segments. The bisector of an angle then would do something. Well, what does it do? Well, it has to be a ray because remember, an angle is a figure formed by two rays. It goes forever. And when we think bisect, we're really thinking cut in half. Now, if you're going to cut that in half and it goes forever, you're going to have to start at its beginning and you're going to have to cut it in half forever. And so it has to be a ray, right? That starts at the end point and goes in the direction that the angle is opening up. So the bisector of an angle is a ray that does something. It's a ray that divides the angle into two. And many texts would say congruent angles, but I use equal the same way I use congruent on angles because the same shape part is given into two equal angles. Or we could say into two congruent angles. Okay? Now, we've got a definition, and so again, we want to focus on the word and what you get out of it. If we're giving a proof when we heard and what you get out of it, The reason we use is definition of that word. Okay? So let's look at how that's going to work here. Given that ray AB bisects angle CAD, we can conclude that this angle, angle CAB, is equal to or congruent to this angle, angle DAB, and justify that with the reason definition of an angle bisector. And the reason we can say definition of that word is because we had the given statement with the word in it and the conclusion statement with the what we get out of it. We had the word and what you get out of it, so then we can use the reason definition of. When we define segments and congruent segments in a midpoint of a segment and the bisector of a segment, we also talked about segment addition. We said something like this: if point C lies between point A and point B, then we could say that the segment AC, which would take us from here to here, plus segment CB, which would take us from here to here, is equal to the whole segment AB. That is called segment addition. Well, just like we can add segments, we can also add angles. And so if we had an angle like angle CAB, which means we have a point on one side C and then the vertex A and then a point on the other side B. And we add to that angle B, notice how we have this common side, AD. Then together we can see visually that they create this whole big angle, angle CAD. That's called angle addition. Now, notice again that that was a postulate. A postulate is something that we didn't take some rules that we learned and some definitions and put them all together in our head thinking about it, doing a little bit of work on paper and reaching a conclusion mathematically that that must be true. We simply drew a picture. If there's an angle from at CAB and an adjacent angle BAD, then together we can visualize that they make this whole big angle, angle CAD. That's a postulate because we can visualize it, logically conclude it without basing it on some other mathematical rule that we've learned in the past. Okay?